Hello everyone, my name is Yanfu ZENG, last year PhD student from the Hong Kong Polytechnic University. My supervisors are Dr. Xinyan Huang and Professor Fu Xiao. And today I would like to give a presentation of my PhD research with the topic of intelligent building fire safety design driven by deep learning methods. And before the start, I would like to thank my examiners as well, Professor Lee and Dr. Hamid Khorasani. All your comments are very useful for me to improve my thesis. So let's get started now. So fire safety provisions such as sprinklers, evacuation plans, or the smoke ventilation, etc. All of these components are very important to protect us from the fire accidents. And the engineers are required to carefully design them and deliver the fire engineering drawings, as well as the performance-based design analysis, such as the modeling of the fire spreading, human evacuation, and structural fire response. So far, there are a lot of advanced computational tools which can help us to conduct the design process. But however, there are still a lot of challenges exist. The first and foremost is that the current design stages are very time consuming. For example, if we are simulate a fire development of 20 minutes, it may take safety few days to get the result, and sometimes even weeks. And it takes even longer, more efforts for the engineers to prepare all the sets of fire engineering drawings. Therefore, the current design is extremely time consuming. And the second challenge is that the fire safety assessment can be affected by many factors. For example, what ventilation strategy has been adopted in our design, or what is the assumption of our fire scenario, like the location of the fire, the heat rate curve, etc. So there are many factors can affect the assessment result, but due to the time-consuming nature, as I mentioned before, it is, in most of the cases, engineers are unable to perform a detailed parametric study and to define what could be the optimal and most effective fire safety management for our building. So therefore, in our design, most of the design are not necessarily the best. And the last challenge is that experience loss. You can imagine just how many fire simulations has been done every year in the world, and how many drawings are prepared. These drawings and simulation data are very valuable. There are many engineering experience and insight inside. But unfortunately, all this data are just singly used. So basically, after we finish one project, all this data just stay in your computer folder, and some of them are never be opened again. And the next time when we encounter a new project, even a similar one, we have to go through all this time-consuming design process again. That will cause a lot of repeated workloads. And moreover, all the experience and insights are not really shared by the whole community or whole the fire engineering society. So therefore, we have to train the engineers again and again, generation by generation. So to address all of these challenges, we are calling for a smarter and more automated design process. And AI could be a promising tool to address all of these challenges. So basically, the feature of AI is that it can learn from the historical data and make the mapping relationships between the input and the output. And after the training, it can provide predictions with intuitive judgment in just seconds. So it has a feature of real-time prediction, and that could potentially help us to speed up our design process. And in my 3-year PhD period, I have done a total of 4 works, which explore the possibility of using AI in the fire engineering designs. We start from the prediction of the smoke motion, which is very important for the performance-based analysis. So in my first work, we try to see if AI can predict the smoke movement, smoke layer descending process in a cubic shaped atrium. And after that, we upgrade our AI model to addressing the rooms that have different floor plans. And in the third work, we'll further upgrade our AI model and see if AI can make predictions for the random building shape. And in my last work, we aim to address and trying to explore whether AI can help us to prepare the fire engineering drawings. So that could be the overview of my research. And now let's dive in the first one. So basically, when we design building, we just wonder, as a designer and engineer, we wonder what would happen if a fire occurs in a building, like how fast the smoke will spread and how high the temperature will rise to, etc. So that kind of process today can be modeled by advanced CFD modeling, such as FDS, Fire Dynamic Simulator. However, as I mentioned before, this computational tools is very time consuming in terms of the simulation time. And back to 3 years ago, we're trying to see if AI can speed up the process. And at that time, we have no experience and we are not confident whether AI can really make accurate prediction. So we start with a very simple geometry, just a cubic shaped atrium. But we still established a very extensive database with over 1,000 fire scenarios, which cover the different atrium dimensions, heat rate, fire locations, and ventilation capacity. So basically, we labeled all the design inputs and also with smoke images, including the visibility, temperature, and the CO concentration at the specific time step. We'll label them and trying to see if AI can get the relationship between them. So the specific AI model we used here is called TCNN, the Transpose Convolutional Neural Network, because we are trying to make a translation from 7 design parameters into an image. So basically, it was a very typical upsampling task where the TCNN can be perfectly addressed to. And after training, we're asking AI to make predictions for some new cases. So here is the very typical case we selected from the testing data set. And for the first row, it would be the prediction of smoke movement by the CFD. And the second row is the AI prediction. We also present the visibility, temperature, and CO concentration result. And they are presented in the video format. So basically, you can have an overall impression like how similar or comparable AI result can be to the CFD. And again, CFD may take a few days to get such result, and AI just 1 second, 1 click. We're also trying to see more results. So we found a benchmark case, again, from the testing dataset, and we trying to use apply different soot yield, heat rate, atrium height, etc. And as you can see in these diagrams, the x-axis is the simulation time, y-axis is the visibility curve from the top descending to the bottom. And the solid lines are the CFD result, and the dashed lines are the AI result. So basically, you can see AI can perfectly cope with all different design conditions. And what we feel is that the AI just work like a non-linear fitting of all the input parameters to the output. Basically, if it has seen the case with a 10-meter height and 20-meter height before, it can give a fitting result with 12 and 15 meter. So with this kind of feature, real-time feature, and we can, as an engineer, we can perform very detailed parametric studies. And to further showcase the capability of AI, we developed a software which we named the Intelligent Fire Engineering Tool, IFE tool. And we also open access it in the internet. So let me just open the, yeah, maybe just wonder if you can see my webpage. So basically in this interface, as a designer or engineer, what do? Is just to fulfill all the information about building and fire. For example, we have a building with 49 meter width, height perhaps 17. I just type them randomly here. Fire size perhaps 4.5. We got fire inside near the wall. So yield perhaps 0.07. We have ventilation capacity with, let's say, 15. Smoke clear height, let's say 3 meters, and just one click. Then you can get all your results, the smoke images. You can also check what could be the smoke development at maybe perhaps 20, 200, or 500 seconds. And you also have the smoke descending profile, which can be compared with your predefined smoke clear height. Then you can have the available safe egress time, which is quite an important parameter when we doing the design assessment. You can also check the other tenability criteria like temperature as well. So basically, if you can also do some quick change of your design parameters. For example, this case is failed. Then we just increase the ventilation capacity, maybe to 5. Then you can find basically the boundary conditions and the optimal solution for your design. So that could be our expected implementation of AI in the future future building design. So we believe that this method can help us to improve the design efficiency and reduce the cost significantly. And of course, with this successful try, we have our second works that we are trying to see if AI can make predictions of fire in different rooms or rooms with different floor plans. So here we labeled the room floor plan with the image, while the white area are actually the indoor room area, and the black area are the outdoor area. So we put our floor plan in this kind of image, and the right side is some examples of our database. So basically, we build all different kind of shapes like L shape, corridor, T shape, cross shape, etc. And also we have the triangle corner or enclosed rooms, etc. So basically, we have over 100 fire scenarios and feed all this data for AI to learn. So basically, for the AI model construction, the input in this work is, of course, the floor plan of the building, of the room, and also the location of the fire, and also the heat rate curve about the fire. So we feed it to the GAN model, GAN model, which was very famous about its outstanding performance in the image generation. And the output would be the temperature, velocity, and soot density fields under the ceiling. And with all this result, we can conduct a performance-based analysis in terms of fire detection time, which I will mention later. So basically, this is a demonstration of our AI result. And we select 3 typical cases. One is the open floor scenario, which means there are no surrounding walls. And the second one is semi-open with both walls and openings to the surroundings. And the third one is a totally enclosed scenario. So we have a result presented with temperature, velocity, and soot yield. And for each case, the left side is the CFD result, and the right side is the GAN result. So basically, we can still find a good agreement between CFD and GAN. And again, CFD takes few days to get that, while GAN just a few seconds. And with all these seeding fields, we can do a detailed fire detection analysis because all the sprinkler, or not all, most of the sprinklers or detectors are installed under the ceiling. And once a fire happened, if we have an accurate estimation of the velocity or the gas temperature of the smoke layer, we can make prediction for the fire activation time, which is quite important for not only the design assessment, but also the sprinkler placement and fire investigation. So one case study is that if we got this kind of fire case and we know where the detector located, we can plot the curve of the temperature and the velocity rise with the time. So in the plots, the gray lines are the CFD result, where you can see a very severe fluctuation, and the black lines are the GAN result, which is similar to aligned to the CFD result. And for the predicted detection time, we can achieve accuracy with 95% average. So that could be another successful try and give us the confidence to have a further step, which addressing the 3D-based prediction, because we know modern buildings, they got all different irregular and innovative building shapes, so that we have to feed all this. We are trying to see if AI can make predictions for the random building shapes. And to achieve that, we, of course, go back to the very first step to prepare enough database. So we have basically the atrium designs with different shapes, and ask AI to learn how the fire can be spread, how the smoke can be spread in all these different geometries. The volume of our database can be ranged from 1,000 cubic meter to 23,000. So for the AI model construction, the input of our AI is, of course, the shape of the building and also the location of the fire. And the output here, we just use 3 visibility slices from the X, Y, and Z directions. So for the X and Y slices, they are the slices across the fire center. And for the Z slice, they are 2 meters above the fire. So the model, specific model we adopted, again, is a GAN model due to its good prediction in our previous study. And this time we also adopt another advanced AI algorithm, which is called diffusion model. And we can compare the results as well. So after the training, again, we select some new cases and ask AI to make prediction. So for the first row are the CFD results, second are the GAN results, and the third is the diffusion result. So after a lot of rounds of fine tuning, we finally got the models that can give us good results, especially for the diffusion model. As you can see, it can even reproduce the fluctuated fire plume, all these flow details. Instead, the GAN may not produce all these flow details. It can, but it has its own advantages of faster computational time. And we're also presenting results for other testing cases here. And for this plot, the x-axis is again the simulation time, and the y-axis is the suit visibility at the height of 2 meters. So basically, the black curves are the CFD result, and colorful curves are the AI. And we can see they still have good agreements here. But unfortunately, not all the results are that promising. For example, for this last testing case with a unique star shape, as you can see in the curves, there are discrepancies between CFD and AES. And from the videos, yeah, you can still see a significant time delay for the AI result in terms of the smoke descending. The one potential reason we believe is that if we go back to the database, we can see this testing case is very distinct with other cases. And as I said before, the AI do things based on the intuition, based on the experience, instead of all the physical laws. So if it haven't seen the similar case before, then it may not provide a good prediction. So that could be the issue. But if you can see, we just have very small with over 20 testing cases in this work, but it can still give good result, at least in 3 different testing cases. So just imagine what if we have a training data with 100, 500, or even 1,000 buildings with different shapes, then the AI could be very powerful. But still, it gives a warning for us that the limitation, we have to make a good aware of the limitation of AI. And every time when we use the AI to make a prediction, we have to check the range of the database so that we can really give the prediction result with confidence. So that is unavoidable. For example, even for the powerful ChatGPT, it can give a very simple mistakes, like wrong counting of the letter of R in the word of strawberry. So we have to aware, what we want to emphasize is that we don't want to say that AI is perfect. It can solve everything in a simple way. But instead, we have to make good aware of its limitation and with better utilization. So that's basically all our efforts on the AI prediction on the smoke motion. And in my last work, we are addressing the drawing preparation task. So nowadays, it relies on the engineers to conduct all the engineering drawings from the architectural plans. However, we want to automate this process. So we propose an intelligent workflow, which start from the information filter, because after an engineer receive the architectural plan, there are so many informations there. We have to remove unnecessary information first, because there are all noise during the AI training process. And we just keep the key information and make them and encode them into a format of a picture or a matrix, because AI can only read numbers. They cannot know what a cat file looks like. So basically, what we expect is that if we feed this architectural input to the AI, it can help us to do all the fire engineering designs. For example, the sprinkler placement. And since all the input and output are in the format of numbers, it will be very convenient for us to perform some code compliance checking. For example, counting the numbers, counting the length, measuring the distance or areas, etc. And after the compliance checking, the engineers may manually make corrections for the design. And after that, we can post-process it to the for the CAD drawings, for example. So that is the proposed workflow for our intelligent design. And in this work, oh, sorry, that's since my PowerPoint is stuck. Okay. In this work, we to verify our proposed method, we did a case study of sprinkler layout design, while the engineers are responsible to provide the placement of all the sprinkler heads, where we labeled in red, and also connected them by pipes, where we labeled in green. And also for the input architectural plan, we made the information filtering and post-process. for all the spaces, such as the office rooms or the corridors, they are presented in the white color. And other rooms that requires no sprinkler installation, for example, some elevator shafts and also some electrical rooms, they are labeled in the gray color. And we also label the riser shaft in the blue, where the pipes should come from. And another prior information we should have is the class of our, the fire hazard class of our building. Because for most of the, basically all of the fire regulations, fire codes, they just divide buildings into different fire hazard classes based on their occupancy. For example, if you are office or shopping mall, etc., then they will specify the spacing requirements between the sprinklers. So that could be a very important prior information for the AI. And the left side is some examples of our database. Basically, we collect a total of 80 CAD drawings. It's not that much, but it's the best we can do, because most of the parties, like the design institute, are not willing to share their drawings. So still, we are conducting the training. Before the training, of course, for the sprinkler out design, we as I said before, most of the codes specify the maximum spacing between the sprinklers. But in practice, it's very hard for engineers to do the design review based on the spacing requirements. So a more convenient, more commonly used way is that transforming this spacing requirement into an equivalent protection radius. And then we can draw the protection area for each sprinkler. And we know that which areas are not really protected. And we can highlight them so that engineers can make corrections, design corrections quickly and conveniently. So for the construction of AI model, the input would be the architectural plan and the hazard class. The AI model we adopted again is the GAN model. And then we expected AI to give the sprinkler placement and as well as the pipeline connections. We add it to the background and do the result evaluation. And that could be the whole process of our AI model processing. Here's some example of our result. We present two cases with the same outline and different interior floor plans. And for engineers, it takes averagely 21 minutes to place all the sprinklers. And for AI, again, it just spent 10 seconds. And if we look at the numbers for the coverage rate and and as well as the total number of sprinkler heads, the AI design could be very comparable to our engineer. But if we look at the result in more details, we can still see a lot of flaws in the AI. For example, the repeated sprinkler placement in the small area. And also some of them could be better if they can be placed in a straight line so that the system can be more organized, well organized. And based on the estimation of engineer, they can make corrections spend about 5 to 10 minutes to make corrections based on the AI results, preliminary result. But still, it was a significant improvement for our design efficiency comparing to the traditional one. Here are more results with different hazard class of low and high classes. You can see the AI can really adopt the spacing requirement. For high class 1, it can place the sprinklers more densely, while the low hazard is they got larger spacing. And for the coverage rate, all of them can be up to 99%. And the number of heads are also comparable to engineer. So now let's look at the result of pipeline connection. So basically, again, this one is not that promised. if you look at them, there are a lot of disconnections in the pipelines by AI, as well as the double or repeated connections as well. So basically, it's far away from the standard quality that we required. And one possible reason we believe is that unlike the sprinkler placement, which have a very specific spacing requirement, the pipeline connections has a larger design flexibility. For example, for the same sprinkler placement, we have at least 3 or even more different ways to make the connections. So this kind of design flexibility makes AI harder to capture all the design rules and patterns. So that's what we are still working on and trying to improve the result in the future works. So that's basically all the 4 works I have done in my PhD period. And to summarize the contribution, we have to go back to the very first 3 challenges of the current design process. And we believe if we are adopt the AI method, we can achieve a quicker and real-time prediction or the generation of the design outcomes, which can significantly improve the design efficiency and reduce the cost. And with this faster prediction, we can also do a lot of detailed parametric studies of our design, and it makes us easier to identify the optimal solution for our design. And more importantly, all the past design experience and data could be reusable. So that could be if our database can be extended to a certain degree, the AI could be very powerful. And of course, as a very first, I think we are the first team which applied the AI method in the building fire safety design worldwide. And of course, there are a lot of limitations, and there are a lot of future works we can still improve. So basically, from the database point of view, this method we believe can be not only adopted in the atrium, it can be also applied to other facilities like tunnels, underground space, etc. So the tunnel is the project what we are working on now in our team. And we are also trying to see if the AI can mimic the human evacuation process as well. From the AI model construction point of view, so far, all the AI model I have used in this studies are purely data-driven, which means the accuracy of the results heavily depends on the data quality. If we have no high quality data, we cannot get accurate result. So to overcome that, one way is to add some physical laws or the rules or attentions in our AI training process. It can make our AI result more controllable and more explainable. So basically, that's a very good way we are trying to improve in our AI model. So from the AI performance point, we believe our AI model still requires validation from the experimental data as well to further increase its credibility and fidelity. And we are also actively seeking for cooperation with with the industry, for example, some by consulting companies or insurance companies, to see whether our tools can be really applied to their practical projects. And if not, how far away we still have between our model and to the practical. We believe there was still a long way to go, perhaps 3 years, 5 years, or even 10 years. But still, we believe it was a very good start, a promising start. And it was really the future trend of the design industry development. Here is a publication list during my 3-year PhD period. And finally, I would like to thank my supervisors for all their support and also thank for the Shu5 project and PolyU to provide me the funding and the opportunity to pursue a PhD degree, and thank all the examiners to providing your comments to improve my PhD thesis. So that's very much all of my presentation. Welcome if you have any questions and comments.